back in chapter 6, at the beginning of chapter 6, we had all these identities, like our fundamental identities. And what were some of the identities we had? Remember them? Some of them? Pythagorean identity was pretty important, right? Like sine squared theta plus cos squared theta equals 1. Or you can rewrite that a bunch of ways, like 1 plus tan squared theta equals secant squared theta. Or cotan squared theta plus 1 equals cosecant squared theta. So those were our Pythagorean identities. And then there were like the reciprocal identities, right? Sine theta equals 1 over cosecant theta. And all that jazz. Cosine theta equals 1 over secant theta. And blah, 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 blah. So anyway, we have all these identities. It turns out there's about 1 million more identities that aren't quite so fundamental, but they're true. Okay, so an identity, if you forget, is an equation that's true no matter what you put in for the variable. Okay, so if you pick any theta, like pi over 6, pi over 4, pi over 10, this equation will always be true. Okay. So these were some fundamental identities. In 7.4, which is the section we're doing today, we want to talk about some less fundamental identities, and we want to talk about how to verify these identities. So the way the problems are going to work in this section, kind of what you're going to be doing is you're going to be taking an equation like this and proving to me that it's true. Or taking this equation and proving it's true. Or taking this equation and proving it's true. Now these are a little simple. Okay, so maybe proving sine theta is 1 over cos theta isn't very difficult. That's pretty much the definition of cosecant. But when I give you a super complicated identity, you're going to have to be able to break it down and get from one side to the other. To kind of show you what I mean, I gave you an example here from a previous class. So this is not a trig identity, but this is an identity. So this is an equation that's true for every value of x and a. It's called the difference of squares formula. Right? X squared minus a squared equals x minus a x plus. It's always true. But what I want to get at here is how would you prove this? How would you verify this? How would you show me that this is true?
X squared minus 1.
So one way to do it, well, the only way to do it is really pick a side. Okay, pick either this side or this side, and hide the other side, and do some valid algebraic manipulation to get from here to here. Okay? So no matter which side you pick, you kind of hide the other one, and say, all right, how can I manipulate this side to end up here? In this particular case, it's a little simpler to start on the right side. And you say, take this expression, this algebraic expression, and what can you do to it just to manipulate it all? What's the only thing you can do with this?
Factor it out.
Distribute, right? Multiply. So if you FOIL this, or whatever you call it, and put the x to the x, and the x to the a, and the a to the a, and the a to the x, you get some polynomial, right? X times x is x squared. X times a is ax. Negative a times x is negative ax. Negative a times a is negative a squared. And then maybe you realize that ax and negative ax are they cancel each other out, right? So these guys go. And you're left with on the next line x squared minus a squared. At this point, you verify the identity for me. Right? Because you started with one side. You did some algebraic manipulation that you learned in another class, right? That we take for granted now, distributing them. And then you ended up with x squared minus a squared. So when I say verify an identity, this is what I mean. Start with one side, perform some operation that you've learned already to get to the other side. So this is what we're doing this whole section, except instead of algebraic identities, you're going to have trig identities. One thing you want to be careful of when you're verifying these identities, you are trying to show me that this is true. So you cannot assume it's true. Like, for example, so there's a difference between an identity and a conditional equation. This is an identity. X squared minus a squared equals x minus ax plus a. This is a conditional equation. X squared equals 4. Right? X squared is not always equal to 4. It just happens to be equal to 4 in this equation that I wrote on the board. Whereas this is always true no matter what x and a you pick. On this equation, if you want to solve it, what would you do? Square root. You can actually do things to both sides. You can say, oh, well, if x squared equals 4, then the square root of x squared has to equal the square root of 4. And you can get x equals plus or minus 2. This is how conditional equations work. And the reason we can do that is because we're assuming x squared equals 4. We're assuming already this is true. Now over here, I'm doing almost the exact opposite. I'm saying, I don't believe this is true. I need you to convince me. Okay? And since we don't know that this is true already, you cannot do things to both sides. It's not logically valid to take an untrue statement, do something to both sides, and say the result is true. Right? It doesn't make any sense. So possibly interesting. So you will never work on both sides when you're verifying an identity. You will start with one and end at the other. If you're doing something to both sides of an identity, you're screwing up, for lack of a better term. That's what this reminds me of. So if we're going to be successful at manipulating, at verifying identities, we need to learn how to manipulate trig functions. There's kind of 4 or 5 basic algebraic maneuvers you're going to have to be able to perform. And I've outlined them here and given you an example of each, so we'll go through these. All right, you're going to have to be able to add fractions that have trig functions in them. Right, you're going to have to be able to decompose fractions, split a fraction up into 2 with trig functions. You're going to have to factor trig with trig functions. You're going to have to multiply top and bottom by the same thing with trig functions. Those are the 4 main ones. But really, the whole trick with identities is that you might have to do something from a math class that you took 5 years ago. Okay? That's why students have a really hard time proving identities, because it builds on every algebraic thing you've ever done in your life. So I'm just picking on 4 that come up all the time. But really, you're going to be responsible for going back and reviewing some algebra as you do this homework and making sure you're on top of it. Let's go through these. So I'm not actually proving or verifying any identity right now. I'm just doing manipulations. All right, example, adding fractions. Write the expression as a single fraction. So I want to take secant x plus cosecant x and write it as a single fraction. The instructions sort of imply that you have 2 separate fractions here. So before you can write this as a single fraction, I'm going to need you to tell me what these are in their fraction form. If I wanted to write this as a fraction with a numerator and denominator, how would I write secant? 1 over cosine. Right? So the implication here is I want you to turn this into a fraction, 1 over cos x. Turn this into a fraction, 1 over sine x, and then add. And I know secant is 1 over cos x because of my fundamental identities. This is from chapter 4, or 6. So the expression secant x plus cosecant x is exactly the same as 1 over cosine x plus 1 over sine x. Now what would I have to do if I wanted to add these two fractions?
Common denominator.
Common denominator. You have to have a common denominator to add fractions. What do you think the common denominator is?
Cosine, cos x.
Cos x sine x. Right? Cos x is one variable factor. Sine x is another variable factor. They have nothing in common. So if you want to add these, you're going to have to multiply a cos x on this side. But you can't just multiply cos x on the bottom. So you have to multiply it on the top as well. Then on the cos x, you're going to have to multiply a sine x on top and bottom. So adding fractions with trig functions is the same as regular adding fractions. You're going to need a common denominator first. So multiply by what you're missing. Cos x is missing a sine x is missing a cos x. So this becomes sine x over cos x sine x plus cos x over sine x cos x. Then they have the same denominator. Cos x sine x and sine x cos x are the same thing. So now that we have the same denominator, we can combine these. What would we get when we combine these? Sine x, you add the numerators. Sine x plus cos x. What goes in the bottom?
Cos x sin x.
2 cos x sin x?
No.
No, just 1, right? You just rewrite the common denominator once. So I've taken my 2 separate fractions and written them as a single fraction, right? There's only one fraction bar. So this is a common manipulation you're going to have to do. So first of all, questions about any of the algebra I did here? Easy? You guys been doing this since you're in diapers? Pretty much, yeah. Good. Second question. Can I reduce this at all right now?
No.
Like there's a cos x and a cos x, so I just can't. No. You sure?
Add it.
Okay, good. All right, I'm just checking. I'm glad that some of you are starting to get angry, because that's how I feel, right? That's how I feel when you cross these out. I'm like, "Arr." Yeah, so since you're adding on top here, you can't reduce them. Next example. Decomposing fractions. Just write the fraction as 2 terms, each with a denominator of 1. So I give you secant t plus 1 over tan t. I want you to write, I've now given you this portion. Okay, I've given you a single fraction. I want you to be able to decompose it and write it as 2 fractions. Write the fraction as 2 terms, each with denominator 1. Okay. So, what do you think? How do you go from a single fraction to 2 fractions? You know how it works? So it's just like if we would have went here and then went in reverse. Right? If you have a sum, if you have 2 things being added on top over a single denominator, you can put the denominator underneath each term. Right? Sin x over cos x sin x, cos x over cos x sin x. So basically it's like a distribution. You can take the tan t and divide it into each term. So you'll get an equivalent expression, but you'll have 2 fractions, secant t over tan t 1 over tangent. And I divided this denominator into both terms on top. But if you look, which is fine, this is legit. This is perfectly fine algebra, right? Division distributes just like multiplication does. So you can divide this to both terms. But I asked you for 2 terms each with denominator 1, and if you look right now, my denominator is tangent. So how do you think I can turn this into denominator 1? Either one. Yeah, so this guy, 1 over tangent, is cotangent. Right? That's the well, that's practically the definition of cotangent, it's the reciprocal of tangent. So if I replace 1 over tangent with cotangent by my reciprocal identity, I've taken care of one of my problems, right? This has denominator 1. It's cotangent over 1. However, I haven't taken care of this other problem. I still have a tangent t on bottom here. What should I do with this?
Same thing.
Flip the tangent up and turn it into a cotangent? I can do that. What else can I do?
Common denominator.
Common denominator.
Cotangent over 1 and then.
So if I got a common denominator and added these, I'd end up back here. Which is okay, but it's not what it's legit, but it's not what I'm trying to get to. I want to keep these separate, but somehow bring this denominator up. One suggestion was to bring it up as a cotangent, and that's okay, that'll work. But I'm asking, is there anything else I can do with these?
Change it to identities and then multiply.
Change the tangent.
Yeah. One thing, another trick that comes in handy sometimes is changing things to sine and cosine. For example, secant t is what?
1 over cosine.
1 over cos t. Tangent t is sine t over cos t. And I know the disbelievers out there are like, oh my God, Josh, you made it so much more complicated. What are you thinking? You're an idiot. But now that I have a fraction over a fraction, what can you do?
Flip and multiply.
Flip and multiply. So you can multiply by the reciprocal. So this 1 over cos t times sine t over cos t, this fraction can get flipped up and then turns into multiplication. So I'll have 1 over cos t times, instead of writing sine over cosine, I'm going to flip it. The cotangent t is just hanging around. Now can I cancel the cos t's? Yeah, because it's multiplication, it's not addition. Right, so cos t on bottom with a cos t on top being multiplied, that's 1. Right, cos t over cos t. So altogether I have 1 over sine t. But again, I want only denominator 1, that's my goal. So maybe I can change 1 over sine t into cosecant. Again, reciprocal identities. And then I have 2 terms, each with denominator 1. This may or may not have been the fastest way to do this. But this is what I was trying to get at. I wanted you to split up the addition, or split up the division across the addition, right? We divided the tangent into the first term and the second term. And then we applied identities until we got 2 trig functions with denominator 1. So this is the kind of manipulation you're going to have to become proficient at. Questions? All right. Factoring. Factor. We love factoring. How come you guys aren't wearing your I Heart Factoring shirt? I know you all have one. I'm going to try to lie.
Do you have one?
Oh, I have like 5. Different color for each day of the week. Factor to simplify the fraction. So sine squared x minus cos squared x over cos x plus sine x. So, the instructions say factor to simplify the fraction. What I want to point out, though, is, like you guys told me last time, this cosine and this cosine cannot reduce right now. And this sine cannot reduce right now. Right? What I'm hoping is if I factor the top, I will get something that matches the denominator exactly. Right? By factoring the top, I might be able to cancel the denominator if I get the exact same thing up in the numerator. So how do you think I factor the top of this? Sine plus cosine times sine minus cosine.
So it's the difference of squares?
Yes, this is a difference of squares formula. You want to think of this like a squared minus b squared. Right? Sine squared minus cos squared is like a squared minus b squared. You know that factors into a plus b, a minus b. So for the sine squared and the cos squared, instead of a plus b, I'm going to put sine x plus cos x. A plus b, sine plus cos. And then instead of a minus b, I'm going to put sine x minus cos. And all of this is still over the same denominator. I haven't touched the denominator at all. Now we can reduce. Right? Because this entire factor, sine x plus cos x, is in the numerator and denominator. It's connected by multiplication here, so reducing is perfectly legit. Sine x plus cos x divided by sine x plus cos x is equal to 1. So altogether you have 1 times this, but 1 times something doesn't change it. This is all you're left. So this happened to be a difference of squares formula here. I mean, what if I would have given you b sine squared x minus 5 sine x plus 6 over, let's do sine squared x minus, it is 2 sine x, you gotta give me a minute, minus 3. If it doesn't work, it doesn't work, but we'll try. So how do these factor? Are trying to simplify here. Right, so on the top, I'm first looking for 2 things that multiply to sine squared, right, which will be sine x and sine x. Then I'm looking for 2 things that multiply to positive 6 but add up to negative 5. Same idea on the bottom. I'm going to need a sine and a sine. But then I need 2 things that multiply to negative 3 but add to negative 2.
Minus 3.
Why they pay me the big bucks. Drop those examples. So the sine x minus 3 on top and the sine x minus 3 on bottom can cancel because you're connected by multiplication. And then you'd be left with sine x minus 2 over sine x plus 1.
And it needs to be the teachers can do that sometimes. pull something in our head that works.
Yeah, sometimes it's just like cool. Can I cancel any more? Sin x, sin x?
No.
No, right? Because I'm attached by addition and subtraction doesn't work. So this is as far as I'd be able to simplify. So as many ways as you could factor back in math, I don't know, 96 or 95 or wherever you learned it, you have that many possibilities of ways you could factor now. You just have sines and cosines in tangents instead of x's and y's and z's. Multiplying by a convenient one. Sometimes, not often, occasionally, it helps to multiply the top and bottom of a fraction by a convenient one, so by the same thing. Multiplying top and bottom by the same thing is like multiplying by 1. So I'm going to multiply top and bottom of this by the same thing in order to simplify the fraction. Usually the thing you want to multiply by is the conjugate. Not always, but usually. A lot of times. Exactly 63%. So what I'm saying is, do you guys remember what a conjugate is or how a conjugate works?
1 minus I.
So for example, here I can build a conjugate by taking the exact same expression but changing a plus to a minus. And my claim is I can simplify this fraction by multiplying top and bottom by that conjugate. Right, so I'm not actually changing the fraction because I'm multiplying by 1. I'm multiplying by the same thing on top and bottom. This is a trick. Okay, this is a non-obvious trick most of the time. So it does come in handy. So what happens here on the bottom? You guys know what this becomes?
1 minus sin x squared.
Yeah, so this is the reason we multiply by the conjugate is because this is a difference of squares and it becomes really nice when you multiply it. Right, if you did your foiling here, you would do 1 times 1 and 1 times sine. And then you would also do sine times 1 and sine times sine. So I'll write it out this one time so you see what happens. 1 times 1 will be 1. 1 times negative sine x, 1 times anything is the same thing. So 1 times negative sine x is negative sine x. Then I move on to this guy, sine x times 1. And then on the end, sine x times negative sine x with sine times sine. Sine squared, right? When you multiply something, you get a square. Something by itself turns into a square. So sine times sine will become sine squared. But I'm kind of wasting my time, right? Because these middle terms are just going to cancel. Positive sine x and negative sine x become 0. So the bottom here is 1 minus sine squared x. And we're using the idea that came from that I showed you at the very beginning of this lecture. If you have a minus b times a plus b, that's always a squared minus b squared. Right, so if you don't want to do this multiplication, you don't have to. This is always going to be 1 minus sine squared. What's going to happen on the top?
Put them together, it's going to just distribute.
Should you distribute the cos squared x?
No.
No! I wasn't expecting no. Why no? I was expecting yes, but it's okay.
Because when the denominator changes to cosine, it'll be useful that way.
The whole point of multiplying by the conjugate is to hopefully get something to cancel. Right? And if you start multiplying this out, it's going to be harder to see what cancels. So you should always multiply where it's helpful, right? Because this is really nice to multiply because it's a difference of squares. Okay? But on top, there's no need. I'm just going to leave it. Oops. Right? These are multiple. is super awesome because we all know from our Pythagorean identities, right, sine squared x plus cos squared x equals 1. And if you subtract this over to the other side, you get sine squared, oh no, I want to subtract this over, sorry. Subtract this sine squared over instead. And you get the equivalent identity that cos squared x equals 1 minus sine squared x. So I can finish my simplification here by replacing this 1 minus sine squared with cos squared. So my fraction becomes cos squared x times 1 minus sine x over cos squared x again. These guys fight to the death because they're connected. This is connected by multiplication. So you just have 1 minus sine x. When you're doing identities, multiplying top and bottom by the conjugate or multiplying top and bottom by the same factor, this is kind of a last resort trick. It's not that it doesn't come in handy, it's just that it's not obvious. Okay, so it's the thing I usually try when everything else doesn't seem to be working. A lot of times you can get away without doing this, right? There'll be other methods you can use to simplify this without multiplying by the conjugate. But those are kind of your basic tricks. Okay, add fractions, decompose fractions, factor, and then multiply top and bottom. Okay. We're all excited. I can feel the energy in there. Like Super Bowl or something. Amazing. So now we're going to actually verify some identities. One of the tricky things about verifying identities is that there's multiple paths to get to the same result. So I can't give you one process that's going to work for every identity always. Okay? The one piece of advice I can give you is that you should only write what is true. If you know it for a fact, you can write it. If you don't know it, then don't BS me. Okay? If it turns out to be false, I'm going to be angry. I think you're trying to trick me. I tried to give you some pointers on how to approach these. You know, if you look at, say, so you have something in mind here, look at our first example. Here's our first example. Verify the identity tan theta cotan theta over cosecant theta equals sine theta. The way you want to approach this, and what I kind of wrote up above, is you want to look at this as a game. You start with one side and get to the other side. Okay? Whichever side you pick to start with is the one you work on, and you do all the algebra and all the fundamental identities you can use on that side until you get to the other side. And you should usually pick the more complicated side, okay? Because the more complicated side is going to have more stuff for you to simplify. So like on this example, if I were trying to verify this, I would pick the left side to start with, because I can do some simplification there. Whereas on the right side, sine theta, it's as simple as it gets, right? I can't do much with it. You know, you want to look for things like factoring, adding fractions, all of those algebraic maneuvers we went over. You want to apply those if you can, right? If it gets you closer to your goal. Every move you make here should be getting you closer to here. If you do something that doesn't get you closer to sine theta, it's useless. If it looks like you're not getting where you want to get, you might just have to start over. Sometimes that happens. That's really annoying on tests. One thing I will tell you on tests as far as identities go, don't be shy. All right, raise your hand and say, Josh, am I ever going to get to the end with this? You know, say, is this going in the right direction? Because if you've made some stupid error on the first step of your identity, you're going to sit there for days trying to figure out how to get that identity to work out, right? So if you want to raise your hand and say, is this going to get me where I need to go? I'll say yes or no. I won't tell you how to do it, but I'll say you made a mistake. You better start over. You better check your work. But anyway, let's just do some and see if we can get a knack to this. All right, so verify the identity. And I gave you tan theta times cotangent theta over cosecant theta equals sine theta. So to verify this, you're going to start with one side and end at the other. We already discussed that we should probably start on the left side. So to actually verify this identity, I'm going to rewrite the left side. And I'm going to do something, anything that gets me closer to sine theta. What do you think I should do?
Use the identity for cosecant.
Yeah, so one trick, since I'm trying to get to sine theta, I might want to replace like cosecant with 1 over sine theta, because that gets me closer, since I put a sine theta in. All right, so one trick that helps sometimes is actually just replace everything with sines and cosines. And if you're trying to get to sine theta, maybe you replace everything with sines and cosines, and then canceling happens. So one valid move here might be to say, all right, well, all of these can be broken down into sines and cosines. Tangent is equal to what? Sine theta over cos theta. Cotangent is equal to the reciprocal, cos theta over sine theta. And then on the bottom, cosecant theta is equal to the reciprocal of sine, 1 over sine theta. Even though this is uglier, it gets me closer to my goal because I have sines in there now. And I can probably do some canceling. What happens here?
Flip it.
Top's just 1, first of all, right? Because sine over sine, 1. Cosine over cosine, 1. Right? Because they're connected by multiplication, I can reduce on top. So altogether, the top becomes 1. The bottom is still 1 over sine theta. But as we talked about, a fraction over a fraction, you can flip and multiply. So I'm going to flip this 1 over sine theta up now.
It's true.
Right, and then 1 times anything doesn't change it, and dividing by 1 doesn't change it. So we've gotten to the other side. That was verified. The tricky thing with identities is you guys are at vastly different levels of understanding, okay? And some of you are going to be able to look at this and see a much quicker path, and some of you aren't. What you need to do when you're writing out an identity for me is convince me you know what you're talking about. Okay? So, for example, a perfectly valid way to do this from the beginning would be, okay, I have tan theta times cotan theta over cosecant theta. Forget sines and cosines. Maybe I know tangent and cotangent are reciprocals. Like 2 1/2, 3 1/3, 5 1/5. So if I know that, what happens when you multiply reciprocals? You just get 1. And then I know cosecant theta is the reciprocal of sine theta. Done. So you can get the same path in different steps. So there's no one way to do it. Sometimes you'll pick the shorter path, sometimes you'll pick the longer path. It just depends on how you think of it. They're both fine. Like I said, only write what's true. As long as you're writing things that are true, you'll be okay. Now be very careful, right? Because some of you, get very, students are weenies, okay? So, you can't just write, you can't just start out with the right side and write, draw some lines and be like, oh, this equals sine theta. Check. Done. Right? You're not trying to get to the answer. You know the answer. You know what you're supposed to get. I'm not giving you any credit for rewriting the problem. Right? I'm giving you credit for showing me how you got there. Right? So don't be afraid to add extra steps. Because that's what you're going to get graded on anyway. Just put a check. Check, done, verified. Did in my head. Okay. 100%.
Are you going to have problems where it's not equal?
I have not, to this day, in my math teaching career, purposely given a false identity.
That's nice of you.
But who knows? I'm getting bitter as I get older. So
We'll start with this class.
start with class after us, Josh.
Yeah.
Who cares about our kids? As long as we survive. All right, let's try another one. So I gave you secant x minus secant x sine squared x equals cos x. Can you verify this idea? What side do you want to start on? The left, right? It's got more crap to deal with. So it'll be easier to try and simplify. So we're going to start with the left and try to get to the right. What can I do on the left? Factor! Factor, 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 factor. Because I know there's a secant x in this term and a secant x in this term. So let me pull that secant x out and see what happens. All right, I'm trying to get to cosine. Maybe this will help, maybe it won't. I can't say for sure yet. But if I pull a secant x out of secant x, I'm left with 1. And if I pull a secant x out of secant x sine squared x, I'm left with sine squared. And in my brain, this is looking very promising. Because I like 1 minus sine squared. Why do I like 1 minus sine squared? Because it's cosine squared. It's identity, Pythagorean identity. Right? You know sine squared x plus cos squared x equals 1. These are going to come up again and again and again. So you better have these memorized. Cosine squared is 1 minus sine squared, and sine squared is 1 minus cos squared. These are all forms of this first Pythagorean identity. So the left side is equal to this factored version. The factored version is equal to secant x times, instead of writing 1 minus sine squared, I'm just going to write cos squared. Super bueno. That helped you.
Makes secant x 1 over cosine.
So if I'm trying to get to cosines, another move right now would be to change my secant into 1 over cosine, right, by the reciprocal idea. So then I have 1 over cosine times cosine squared. That simplifies, right? That reduces. Cosine on bottom, cosine times cosine on top. So this cosine, there's 2 of these, it's going to eliminate 1 of them. Right, so right here, I really have 1 over cos x times cos x cos x. Right, if you think about what the square means, it means you had cos x cos x. So the way this reduces, one of the cosines goes away, you're just left with that. So this is one way to do this problem. Does anybody else see a different way? Does anybody else try a different way? Or do you see a different way now?
You can multiply the secant by the cosine squared and then divide the cosine squared by the cosine on the other side of the equal sign. Yeah, you could, because then you would have 1 over cosine and then it would be equal to secant.
You can never divide by both sides in an identity. You can never move things from one side to the other side. But if you take this side, you work on this side. If you take this side, you work on this side. You never
No. I mean, like, once you get past that and you have the cosine squared equal to cosine.
No, it's not. Why? Why is it equal to cosine? Tell me why.
Well, if you wrote the rest of the equation right before.
No, this isn't true. You can't write it like it's true. This isn't true. I don't know that it's true, so I can't put equals cosine here because I don't know that it equals cosine. I see what you're saying, and at the end of the day, you'd get a true statement, right? But that's not formally how you prove these. You know what I mean? That's not logically okay.
So we could just kind of pretend that we don't have the right answer.
Yeah, that's
And then
more.
we're trying to find it.
Right. That's more the way I would like you, at least for now, to play this. You know, as you get better at this, you can manipulate one side and manipulate the other side and make them match up. That's okay. But for now, I'd really just rather you start with one side and do nothing but that one side until you get here.
Until you get the final answer and then verify it with the other side.
Yeah, so verifying is getting to the other side. Right now, we can't assume it's true. We can't write it all the way down because it's not necessarily true yet. But there is another way to do this, getting back to my original question. There's always another way to do it. You could start from the beginning here writing out your secant. Right? Maybe you say, I'm trying to get to cosine. Cosine's my goal. So maybe I put 1 over cos x in immediately. How does that play out? What happens then? What's 1 over cos x times sine squared? Yeah, remember when you multiply fractions, you multiply straight across. So if I decide to put in 1 over cos x here, these would get multiplied straight across and become sine squared x over cos x. And now I have two fractions with the same denominator, so how do those add? Combine the numerators, but leave the denominator the same. And then on top I have an identity. 1 minus sine squared can be replaced with cos squared. Cos squared over cos. Cancel 1. So there's usually multiple ways to get your result. Go either way on this one. I don't think either side is going to be very much easier than any other side. So what do you guys want to start, left or right?
Right.
I think they're right.
Whoa, 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 all right guys, calm down. I don't need any fights breaking out here.
And you can't move anything to the other side, or can you? Not dividing, but adding. Like we wanted to add the cotangent to the other side.
If x equals like a, then x plus b equals a plus b. This logically is true. But if we don't know this is true, we cannot conclude this. So since I don't know, since I'm pretending that I might have a false identity here,
so you have to treat them as separate entities.
Yes. Until you get from one to the other and know for sure.
So you pick a side and you just kind of blink out the other one. Doesn't exist.
Yes, so let's pick the left. Because I don't know. I've always wanted to be right. So I pick the left side.
I'm sitting next to two lefties.
Oh. Another reason, I guess.
Always.
If I decide to pick this side, what can I do here?
Divide each term by sign.
Yeah, divide the sign into each term. That's kind of the only thing I can do here, right? I mean, I'm trying to get to two separate terms, so I'm going to divide the sign into each. Sine goes into one, sine goes into cosine. So it'll become, by decomposing these fractions, by splitting up the fraction, it'll become 1 over sine minus cosine over sine. And then comparing what I have to what I want tells me I'm pretty much done. Right? Because 1 over sine is equal to what? Cosecant, reciprocal identity. Cosine over sine is equal to cotangent, quotient identity. Right, this was reciprocal identity, quotient. So I got where I wanted to get. So it's true. If you started on the other side, it would be pretty much all the same steps, just in reverse. Or if you started with cosecant minus cotangent, then your first step would be to break those into sines and cosines. So you go this way. And then you'd have to add or subtract these two fractions, getting you back here. So it doesn't, it's the same amount of steps no matter which side you take. I'm going to do one more. I want you to go. I'm talking about that. Yeah.
Good one.
Verify the identity. So, sine x over cos x plus 1 plus cos x minus 1 over sine x equals. This is my identity. This is what I want to verify. Prove. Establish. What side should I start with?
0, right?
0, right? There's so many ways to go from there. All right, so pretty clearly, unless you're like a masochist, pretty clearly you're going to start from the left. What do you think I should do here? Same denominator. My hope is that if I can somehow combine these two fractions into one fraction, everything will cancel as zero. That's my hope. So in order to combine these two fractions, I need a common denominator. So what should I multiply this guy by?
Sine x.
Right. He needs a sine x. He doesn't have any sine x in the bottom at all. So I put sine x. Sine x. All right, I multiply by sine x over sine x. Now, this denominator does not have the cos x plus 1. So I put cos x plus 1. Cos x. So on top here, so let me do this first fraction. Sine times sine will become sine squared x. And on the denominator, you don't have to multiply it out ever. When you're doing common denominator, you can just leave it sine x times cos x plus 1. Now on this second fraction, I am definitely going to want to multiply out the numerators.
Difference of squares.
It is a difference of squares. All right, cool. I like that. So what am I going to get when I do cos x minus 1 times cos x plus 1?
Cos squared x minus 1.
Cos squared x minus 1. Because the middle terms will cancel. Cos times cos gives you the cos squared, but then when you do cos times 1 and minus 1 times cos, they cancel. So then all you have left is negative 1 times. Like you said. Okay, and what about on bottom? Well, the common denominator, right? Not yet. Will be soon. So now I have the same denominator, which means I can push them together. Sine squared x plus cos squared x minus 1, right? I just wrote all these on the top. Over, who cares? It's not going to matter. Right, because what's happening on top here? Pythagorean identity, sine squared plus cosine squared. If you remember nothing else, you should know that that's 1. So on my next step, I'm going to replace sine squared plus cosine squared with 1. So this next step will have 1 for sine squared plus cos squared, but then minus 1 all over whatever, the common denominator. The top is 0. And 0 over anything is what?
0.
Right, 0 divided by whatever, 0.